program. नमस्कार सर पटकी साहब.
नमस्कार, गुड मॉर्निंग.
हाँ सर, वो अभी ऑलरेडी मोर देन 25% आ चुके हैं, तो नाउ वी कैन स्टार्ट.
यस.
एंड फॉर पार्टिसिपेंट, आपकी नॉलेज के लिए कि पटकी साहब कल का थोड़ा सा रिव्यू करेंगे पहले, सो दैट कि आपकी जो कल पढ़ाया था वो फिर से थोड़ी सी मेमोरी में आ जाए. और आफ्टर दैट फ्यू क्वेश्चंस यदि आपके छूटे होंगे कुछ तो वो लेंगे. एंड आफ्टर 15 मिनट्स न्यू टॉपिक्स वो शुरू करेंगे. फर्स्ट 15 मिनट्स कल का रिव्यू एंड क्वेश्चन आंसर्स करेंगे. तो ऑल द बेस्ट टू ऑल द पार्टिसिपेंट. माय रिक्वेस्ट अगेन दैट जैसे कल आप लोगों का पार्टिसिपेशन रहा था, टुडे भी आपका पार्टिसिपेशन वैसा ही होगा. और बेटर ये होगा कि जो प्रोटेक्शन से रिलेटेड कुछ भी प्रोजेक्ट में जो आप लोग फेस प्रॉब्लम्स कर रहे हैं, उन प्रॉब्लम्स को यदि आप ज़्यादा डिस्कस करेंगे पटकी साहब के साथ और उनके व्यूज लेंगे तो ज़्यादा अच्छा रहेगा. ऑल द बेस्ट फॉर टुडेज एंड ओवर टू पटकी साहब फॉर टुडेज प्रोग्राम.
Yeah, thank you, Lambaji. So good morning to all the participants. Welcome to day 2. And yesterday on day 1, we in the morning session we looked at what grid discipline means. Basically, we saw the provisions which are made under the Indian Electricity Grid Code (IEGC) and how progressively amendments were made to improve the power system operation and keep the parameters under control in a very narrow band. As especially you can see the Indian power system from a deficit to surplus. This journey actually gets reflected into the reliability parameters in terms of stability of voltage, stability of frequency, and the loading of various corridors. Though I would say loading of corridors still much to be done because the generation growth and the transmission growth, they do not really keep in pace with each other, and so that's why congestion issues still arise in certain areas. Though the generation availability has increased, there is a surplus now available which enables us to now even activate automatic generation control as a secondary control for frequency. There are areas of concern related to voltage control, especially in terms of firm policy on reactive power management and how the voltage can be kept under control. There are areas still in pockets where voltages become at a full load condition and voltages become high in light load conditions in the night time. Of course, there are mitigation measures we discussed by way of compensation, reactive power compensations which are being done. We talked about stability of the grid, how the power transfer equation can be used as a reference criteria for deciding the power flow capability in a corridor, and it is crucial to control X, which is the impedance between the two terminals. It could be generating station at one end and remote transmission station at the other end, or it could be between one transmission area to another transmission area. And we also saw as the X value goes up, the system becomes weak. So number of lines which operate in parallel actually makes the system very strong. So we should at any cost, when the grid is, prevent line tripping and the phenomena of cascade tripping which has been experienced in the past. I think with the improvement in the protection and control measures, now that has become much less frequent. The last major shutdown was in 2012, and number of measures which were taken subsequent to that have started giving results in terms of better reliability of the power system. From the CA side, there are a number of improvements done on the technical standards. There is a draft reliability standard also, which spells out what each constituent of the power system should do, what generating station should do, what transmission station should do, and what a distribution company should do to maintain the grid discipline. And we have seen the frequency band getting narrower and narrower, and at present it is being operated between a very narrow band of 49.9 and 50.05. And full governor mode of operation with AGC control is now being implemented. Indian power system also now has ancillary services. We had a discussion on that yesterday. Ancillary services are basically the resources who volunteer to provide support for keeping the frequency within this narrow band. They can be independent power producer. It can be hydro units who are otherwise not running because of, say, conserving the hydro resources, or there could be other power station like gas-based stations who in merit order are not getting dispatched by the load dispatcher. So these are the incentives being given so that grid frequency can be maintained, and commercially it can be then justified. The cost can be justified. Same thing goes for the voltage support, and still we have a long way to go in terms of voltage support. And we saw how the generator capability curve can be used to the optimal level without jeopardizing the equipment health. Support can be provided to the grid to support the reactive power management and also the active power management. Similarly, ancillary services includes after the shutdown, the restoration process by way of black start capability, and there can be commercial incentives given even for the stations which can provide such a support during black start. So these are some of the things which we discussed yesterday, and we also refer to various technological developments which are enabling with some capital investment, improvement in the reliability, etc. We talked about flexible AC transmission system where static war compensators, STATCOMs, there can series compensators, shunt compensators, or even unified power flow controller or phase shifting transformer, how they can be effectively used to increase the capacity of the corridor, so that same corridor can carry more power within the thermal limit of the conductor. And surge impedance loading, and what is the effect of loading beyond the surge impedance and loading below the surge impedance. So we saw that yesterday, and we also talked about various special protection scheme, especially under frequency load shedding scheme and other schemes, how demand management, demand forecasting, generation forecasting, the role of renewable energy, etc., how it is taken care in generation. This is basically the overall summary of yesterday's deliberation. So if there are any questions, we can now discuss some of those questions before starting the topic for today. So we will spend 5-10 minutes for questions. So anybody who has any doubt or questions, we can discuss. Anyone?
No question as of now, sir. When it will
Okay.
come, we will raise the question.
Okay. Okay, is my screen now visible to everybody?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes. So today we are going to discuss power system analysis under contingencies and what are the measures for catering to different contingencies. Because however good planning you do, and there are the guidelines for generation planning, distribution planning, etc. Which in the design itself, there are certain measures taken so that for certain contingencies, network still operates in a normal way. But power system is such that in spite of all the measures, there would be incidences where certain contingencies will require some automatic interventions or manual interventions. So that is what we'll see today. So analysis of the grid conditions and factors affecting operation of the grid and simulation of the system conditions corresponding to critical operation condition is expected to be done on regular basis and suitable operation strategy is to be worked out. This is the role of load dispatch center. Generally, this is done based on the real-time data from the network every day. State estimation program and load flow program is run periodically and with respect to the line loading, etc., it is ensured that adequate margins are available if any unforeseen tripping happens. And in case that tripping happens, what will be the sort of new condition of the grid that can be found out by running such a study. So this is a regular feature in the national level load dispatch center, regional load dispatch center, and the state level load dispatch center, where this contingency analysis by stability studies on real-time network, that is the most important thing. Normally you do the study based on the network parameters in an offline mode, but here you actually take the real-time values from the SCADA system and run the load flow program and the state estimation program to get the realistic picture of what is going to be the scenario if some contingency happens. With the experience of 2012 grid collapse, there was an amendment in the planning criteria for transmission, where it was said that while n-1 or n-1 minus 1, that means already you have given one outage and then the second tripping occurs, the security requirement should be taken care of. Normally, the criteria for planning is n-1 event. All parameters should remain normal. Nothing should be required to be done for one force outage, for example. But if there is a double contingency, that means after n-1, if there is a one more force outage, then perhaps some manual action will require to be taken. Or if there are multiple contingencies, then some automatic actions will be required to be taken. So this is again done in a planned manner when you design a system. Very often we though the planning wise certain things are envisaged, in practice the network gets modified because of certain unforeseen loads being fed or unforeseen conditions of say load drawal. we very often hear in terms of grid discipline that certain region has overdrawn as compared to the schedule. It happens in for catering to say agricultural load or due to some environmental condition. Suddenly one region may start drawing more power than what it is scheduled. So in such contingencies, certain measures need to be triggered automatically. In terms of frequency, we have already discussed this aspect. These are some of the recommendations of a report of CA committee who had recommended narrowing of the frequency band to bring in more discipline in following the schedule and the actual drawal over the network. And this is now being tightened further as we discussed yesterday. The mechanism for settlement of deviation would also require a change from frequency linked UAT tariff regime to a system of settlement in kind and penalty for exceeding deviation from the specified limits. So this was basically the learning from the UI regime, and going forward, as we saw yesterday, the recommendations for IEGC for 2020, that unless the FGMO and ancillary services are introduced along with the tight frequency band and real-time balancing mechanism, the stable frequency operation will be difficult to achieve. So this was a committee opinion some years back, and exactly the same thing has now been being implemented. Yesterday, as we saw, that full governing mode of operation along with ancillary services is being implemented, and as a result of that, and also as a result of our system becoming stronger in terms of generating resources, where we now have reserve capacity online available, is possible to implement even a narrower band. And the IEGC 2020 recommends that now the frequency band to be tightened even to now 49.95 instead of 49.9 to 50.05. Integration of the renewable energy in the grid continues to be a challenge. The penetration level, which is in terms of energy, which is around 9 to 10%, is likely to go up by 2030 to almost 30%. And if that is the level of penetration of renewable energy, lot more planning will be required in terms of tackling the variability of this generation, because almost 30% of the energy, if it is becoming infirm, then managing the schedule will become even more challenge. And that's why you see a lot of discussion now taking place along with the distributed renewable resources, the energy storage mechanisms might be required to be implemented to begin with at the distribution voltage level, and later on maybe at the sub-transmission level, so that there is a support available to tackle the variability on a real-time basis and with a fast enough response so that frequency can be maintained. Otherwise, the present balancing mechanism in terms of primary control, secondary control, and tertiary control, the time to respond, as we were discussing yesterday, it's in even the primary response is up to 15 from 15 seconds to 15 minutes, and then the secondary response, and followed by the tertiary response, which is manual. So that sort of a time in terms of response to do the balancing of the generation with the given load condition will not do the required frequency control, and hence the storage becomes necessary. Controlling high voltage in the grid during periods of low line loadings. This is still a problem. High voltage in the grid during periods of low line loading. After you exhaust all the reactive power support, there is a need to open 400 kV lines. And yesterday I had mentioned that typically a 400 kV line of 100 kilometer injects 55 MVR roughly as a thumb rule into the grid. So this causes rise in the receiving end voltage because of the capacitive reactive leading reactive being injected into the line, and the voltage goes up, which is called this Ferranti effect. So this high voltage prevention is done by then opening the lines during light load period. But we have to remember that when you open the line, you are actually weakening the network if some contingency happens. That means even in the night time, suppose the lines are kept open and we saw the system stability will get compromised by keeping the lines out. So on one hand, you want to control the voltage, but on the other hand, you are sort of taking risk of instability in the system. So this is the sort of a balance which has to be very carefully chosen. So as one of the measures is number of installations of shunt reactors in the grid to control high voltage conditions. So then the type changing of the transformers especially at the generator transformers will help, and also taking advantage of the reactive capability of the generators by controlling the excitation system will have to be more effectively used. So the generator should participate more effectively in voltage control, reactive power support. This is again the statement from CA report that it is also observed that generators shy away by providing full reactive support under the pretext that these operating conditions limit their capabilities due to the fear of overheating of the generator end region, and under this operating condition, especially when you absorb reactive power, people are hesitant to provide support. But perhaps as ancillary services with a financial incentive, this sort of a risk generating stations would be incentivized to provide support. So this is what additional tariff incentive may need to be considered for facilitating operation of hydro generator in synchronous condenser mode. We discussed yesterday what all modifications are required to enable synchronous condenser. If the new plant is being built of more than 50 megawatt capacity, then of course now it is a technical standard mandates that synchronous condenser capacity should be designed. Even the old powerhouses we can retrofit to enable this operation with the necessary modifications which can be done. And as I mentioned to you, this is again a statement from the report of CEA that it is also necessary that schedules are issued so that transmission lines are loaded to their capability. Conservative approach in loading the transmission lines would result in high voltages, and opening of the lines to control the over voltages will result in depleting the transmission capability, and it will be underutilization of the available generation capacity. Apart from high voltage, we also face the low voltage problem. Again, these are the statements taken from the contingency planning report of CEA, where it is said that parts of the northern grid, specifically Punjab and Western UP, Uttarakhand, and J&K faced severe low voltage problem, especially in July to September in Punjab during winter months in the hilly areas. There is a need for installation of adequate shunt capacitors to address the issue of low power factor of these loads. SVC schemes are under implementation, which would address this issue to some extent, and further application of STATCOMs, which are state-of-the-art equipment for providing dynamic power support for better voltage stability should be considered. So based on this recommendation, again, there are implementation plans for SVCs and STATCOMs. A reactive power support by generating stations we have already discussed. I will only read out again the last bullet from the report, which says that task force recommends that full reactive capability of the generator should be available for voltage regulation, and there should be mechanism to compensate the generators for any loss of active generation in the process of providing required reactive support. So here it is sort of prioritizing the reactive power support when it is critically needed for the grid stability against the loss of MW to enable that. We saw in the capability curve yesterday that the reactive power capability somewhat gets reduced as you fully load active power. If you remember the shape of the curve in the overexcited region, the full reactive capability can be achieved at 0 MW. That is the maximum. But as you pick up active power, the reactive power to some extent reduce. This is basically to control the overheating of the armature as well as the core of the generator. This restriction is required to be maintained as per the capability curve. Next is the tuning of power electronic devices, which includes secondary controls which are implemented through governor, supplementary controls during specific conditions, and FACT devices, HVDC and FACT devices, various controllers which are there by way of series compensation, shunt compensation, unified load controllers, etc. So these sort of devices can provide dynamic compensation with the automatic schemes. These automatic schemes need to be conceived depending on a certain contingency, wherein these controllers can effectively compensate the contingency so that systems stability margin can be improved. And same way, yesterday again we are mentioned in the excitation system, we have got power system stabilizers. So depending on again the inter-area oscillations which are experienced, to help damping of those oscillations, the power system stabilizers can be effectively tuned. And all these being dynamic devices, they need to be tuned as the network changes happen. So periodically, these sort of devices will require to be reviewed based on the actual system condition, so that the corrective action becomes more effective. Protection coordination also becomes one critical aspect, that all utilities should follow the guidelines and get the protection systems audited from time to time as per the recommended methodology for relay settings, data format, and checklist as specified. So again, this is again statement from the CA's report on the contingency planning. For different contingencies, if there are any setting changes which are necessary for coordination of control actions with respect to the protection schemes, this becomes important, so that there is no undesirable protection operation. And we'll discuss more in detail in the afternoon session. What are the protections which are susceptible for undesirable operation during system disturbances? So database of the settings of various relays also needs to be created, kept updated and verified during the relay audit. The database may be maintained with the regional power committees. One of the observation after in the 2012 grid collapse is there was a number of location discrepancy between the actually adopted settings compared to the recommended settings by the planning group or whoever is responsible for protection planning. So this audit will reveal such deviations. In the numerical relay, many times this being the digitally programmed, all the settings. Hello.
Hello.
Hi. Yeah. So many times during testing or any other commissioning activity or some modifications being carried out by the OEMs of the protection suppliers, some changes in the settings are not restored back after testing is completed, and this results into certain undesirable operations. And to control such a thing, this audit will actually help. But we have really not gone to the level of protection audit where you can verify the line by line the complete setting program, which runs in hundreds of lines actually. Unlike the earlier version of static relays or conventional relays. So there is a need to do this in an automatic way, where the soft file of the recommended setting is compared automatically with the actually loaded file into the relay. And this is what basically is the recommendation of the task force, so that actual verification of every parameter of the setting can be done. When the system has major contingencies and the system is weakened, when any event gets triggered, to prevent total collapse of the grid, it is desirable to split the grid in a controlled manner. This is called control isolation. And this control isolation can be achieved through planned islanding scheme. And it was mandated that all the major cities in India should have islanding schemes, so that in case of grid disturbance, power supply can continue without any interruption in the critical areas. So number of islanding schemes are proposed and already are in service. but the success rate for a islanding scheme depends on many factors. For example, when the islanding scheme for Delhi, when it was being worked out after 2012 grid collapse, it was observed that the proposed islanding scheme, opening of large number of elements is required to isolate the region, because there are number of interconnection points with the grid. And for the island formation, all the elements connecting to the rest of the grid have to be opened simultaneously. Failure in simultaneous opening of the interconnecting feeders can happen due to number of reasons, including failure of the communication or undesirable opening, and this may jeopardize the success of island to survive post initiation. Another thing which happens is, within the island there would be generation and load imbalance, and island may not survive. So these are some of the concerns which need to be addressed when the islanding schemes are planned. These are some of the recommended settings for under frequency load shedding scheme, and then triggering the islanding of the area. So these are the various levels at which the islanding is recommended. So this is actually summarizing of the report of the task force on the power system analysis under contingencies. Any questions on this topic before we go to the next topic? On the contingencies, as pointed out in these sections. You can spend few minutes on the questions on this. Yeah, any question?
No, sir.
Okay. If any question is there, you can still ask at the end of the session also.
Namaskar, sir.
Yes.
This is Apurva Roy from Parvati Power Station 3. I have a question regarding power system stabilizers. Can you please elaborate about the equipments, power system stabilizers? What are these?
Yeah, power system relates to inter-area oscillations due to what is called small signal instability. There could be continuous hunting or oscillations of MW. And some of you who are posted at the power station might have experienced this phenomena, where you see the generators active power oscillating at a very low frequency. Typically, frequency of oscillation is 0.1 hertz to 1 hertz. And if this is not controlled in time by some remedial action, there can be a then greater power swing type of phenomena which will result into out of step operation. Now, to prevent this sort of oscillation to continue for a long time. Power system stabilizers are mandated to be provided for all hydro generators of 100 megawatt and above, and all thermal generators of 250 megawatt and above. Basically, what it does is it senses the frequency and magnitude of the oscillation, and accordingly counterbalances it by creating oscillation in the excitation system. So the excitation system oscillation acts as a damping force on the active power oscillations, and this helps in stabilizing the grid. So this function, which is part of the excitation system, is called power system stabilizer, and all the units which are of the said size, that is 100 megawatt and above and 250 megawatt and above thermal units, they all need to respond to these oscillations so that these oscillations can be damped out. That is the purpose of power system stabilizer. Is it?
Okay, sir. Okay, sir. Thank you, sir.
Okay, now let us talk about blackout. Blackout is actually extreme condition of a contingency. Usually it happens with one or two contingencies, that means one line tripping or two line trippings, and then there's a cascading effect leading to total shutdown. Some of the causes are here given: pre-existing conditions such as generator or line maintenance and heavy loading. Usually the force outages of any line due to, suppose for example, line is had to be taken out in spite of the loading of the transmission corridors because of some say clamp is becoming hot. So emergency force outage is required to be taken. So it results into again a double contingency, because system is already loaded and then you are required to take one more line outage. Or sometimes there is a pre-existing condition where the line is out for major maintenance or construction activity, or some reconductoring activity, or sometimes you do loop in, loop out, or a conductor replacement, etc. So there is a long pre-existing condition which has depleted the transmission system, and then some force outages happen due to fault, etc. So this results into again a disturbance which can lead to grid collapse. Next is insufficient reactive power support. We talked about need for reactive support, but if the support is insufficient, there can be a voltage instability by voltage collapse phenomena, and we had discussed at length the power versus voltage curve of the transmission line. So this is another common cause. Earlier, when such a phenomena used to happen in distance relays, line used to trip on three-phase fault. Actually, the reduced voltage and increased load used to result into activation of the zone 3, and three-phase fault in zone 3 used to be a reason for tripping. So usually engineers used to report that this tripping is on account of power swing. But of course, with the new numerical relays, understanding has improved, and there are features to tackle which we'll discuss in the afternoon. Inadequate right of the way for maintenance is also one of the reason for the contingencies of depleting the transmission corridor. Insufficient monitoring of the line loadings, etc. Inability of operator to respond to impeding disturbances, like it happened in the 2012 case also, when the excess power was being drawn under certain 400 kV lines. The I would say geopolitical processes are such that with the agriculture season, giving shutdown to certain areas becomes a socio-political issue, and the decision making on manual opening of the tie lines becomes very critical. And in the process, then automatic action by way of tripping takes place. Of course, so this inability of operators, though they know that line overdrawal is taking place and line loading is increasing, decision to open the line sometimes become a critical factor in prevention of grid collapse. Of course, inadequate planning and operation studies and lack of automatic actions is basically one of the reasons, because it has seen that in system disturbance, manual intervention from the operation engineer is sometimes not possible, humanly not possible, because the time required to take a corrective action in a manual way is not sufficient. So automatic schemes are necessary in such cases. So this is a sort of a hierarchy of various contingency schemes. You can see at the base is all your under frequency scheme, under voltage schemes, out of state protection schemes, etc., etc. These are the foundation of special actions. Above that, then comes the special protection scheme. A typical special protection scheme is, say, overload based or contingency based, and we'll see some of this scheme, special protection. Next becomes the remedial action system. These remedial action systems, again, there are a number of ways where you can create sufficient margin so that unstable operations can be, risk of unstable operation can be minimized. And finally, the schemes are called system integrity protection scheme. In spite of all these level 1, 2, 3, if we are not able to prevent certain abnormal conditions, then you need a system integrity protection schemes. And one typical nature of this sort of a planning is there are multiple constituents who are involved. It's not that these schemes can be done only between one utility, but there are cooperation and coordination is required between different constituents, and that is the role played by the regional power committees, who will coordinate with all the constituents so that these schemes can be implemented. And some of these schemes may have remedial actions to be taken and at a far off area, though the event is taking place in one area, but the action to be taken would be at a totally different location. So a good communication network is also required. That's why even the communication network is shown in this figure with the GPS support. So these are the sort of new technologies, and to do this, phasor measurement unit PMU are being deployed in the power system at 400 kV level and 765 kV level. So special protection schemes, as I mentioned, these are the schemes which are designed to take care of the system parameters within their normal limits and preserve the system integrity within the tolerable range of the parameters. very large number of possible operating contingencies in the modern electrical interconnected power system. Now, when the regions were not interconnected, the effect of one region on another region was very minimal. Even if you have, say, DC interconnection, then also there is a sort of isolation of disturbance from one region to another region. But with the AC interconnection, with all the regions, with Indian power system operating in a synchronous way as a single area, there are very large number of possible operating conditions for which you need to plan measures. And that's why this complex contingency and state estimation programs need to be totally automated so that actions can be done in an automatic manner. And again, the phasor measurement unit and its technology is going to play a larger role in future. Unpredictable changes due to evolving nature of the power system is basically arising because of the renewable generation. And as I was mentioning, the renewable generation contribution, which is today in terms of energy, which is just about 10% today, is likely to be 30% by 2030. So it will be very significant renewable energy presence in the grid. And by very nature, it is unpredictable. Though, of course, there are methods of forecasting renewable generation, including solar and wind, but there are inaccuracies on those, and there will be unpredictable changes for which we need to be prepared. And I had mentioned that storage is one of the solutions which is being looked at. One of the distinguishing features of this system integrity protection scheme from other protection scheme is the fact that actions taken by SIPS will go beyond isolating the faulted element and will seek to preserve the stability, security, and integrity of the entire power system. So these are all termed in terms of technology as wide area protection. You must have heard the terminology in PMU. These are called wide area protection because this is not only, action is not just confined to one area, but it will encompass multiple areas or even the entire power system as far as the remedial actions are concerned. This is again the features which spelled out. Again, these are some of the standard definitions. SIPs may monitor the power flow on the transmission line in a certain boundary, which is basically tie line flows. But in the event that these lines are at risk of thermal overload, keep the suitable generating assets in the location which is totally away from this transmission line. So actions can be tripping of the generating units, or it could be shading certain loads at a totally different location. Because when you talk about 400 kV level, local actions may not be giving sufficient relief. This is again a clause from grid code. It says the planning criteria is based on the security philosophy on which the interstate transmission system in India has been planned. It states that as a general rule, the ISTS shall be capable of withstanding and be secured against certain credible contingency outages without necessitating load shedding or rescheduling of generation during steady state operation. This criteria is basically known as N-1 criteria. So this is a provision in the grid code and technical standard. This is the typical representation of a special protection scheme, where there is a disturbance which triggers power system certain parameters to change. There is a sensing of these parameters, or it could be direct detection of an event. For example, a tripping of certain tie lines of, for example, some HVDC corridor which is carrying say 1000 megawatt suddenly trips. So that tripping itself can detect and initiate a special protection scheme. Or because of tripping of one tie line and loss of that power flow, the power flow will get diverted and overload certain other lines. So you can take overloading of other line as the criteria and then trigger the special protection scheme. So that is the two ways of triggering the special protection scheme. And this sort of signals become input. Then there is a decision-making process, and there is a remedial action, which is again implemented in the power system using the existing SCADA systems for implementation of actions. So these are called response-based or event-based. Response-based means certain parameter exceeding some limit, that is response-based. Event-based is say tripping of tie line or bus fault occurring at some station can be event-based scheme. And now, what are the possible actions the special protection schemes can do? It can do generator rejection. Generator rejection means suppose there are 4 generating unit, you trip 1 or 2 generators so that loading can be brought under control of certain evacuation of the power, if that is the issue. You can do load rejection. Load rejection typically may not give relief to all the generating units where loading of the line is concerned, evacuation corridor. In that case, generation tripping along with load rejection, both will be required. Then there are possibility of system separation. If one area is causing overloading to another area by excess power flow or unscheduled interchange is taking place, you can open the tie lines. So it will result in system split. But splitting the system is better for survival rather than syncing together. So that is basically a strategy. Instead of tripping of generators, you can run back the generation. So running back of the generation could be by the action on the turbine control valve on the steam turbines, or it could be inlet valve control on the hydro turbines. We can have actions due to out of step relaying. Again, this is something which we'll discuss in the afternoon more in detail. Excitation controls, generator run back, power compensators to be triggered automatically, or combination of all these different type of schemes. So all these can be done as a special protection scheme. There are some of the examples just for the purpose of illustrations. This is one of the papers which was published by NLDC, which had listed out some of the schemes after the implementation. You can see most of the schemes. For example, the first scheme which I mentioned is load shedding in southern region and generation rejection in eastern region, subsequent to tripping of the HVDC Talcher Kolar bipole. This HVDC line, if it trips, then there is a load rejection in southern region and generation rejection in eastern region. So this is one example where, as I was saying, the power system element is a HVDC line between Talcher and Kolar, but the actions are taking in the southern region and eastern region, which are in totally away from the element which is under fault. Second scheme is load shedding or generation rejection within northern region, subsequent to tripping of the HVDC Rihan Dadri bipole. Again, similar example. Again, a major tie line has tripped or power flow got disrupted. So you are doing in the northern region the load shedding so that flow on other balanced lines which are remaining in service can be kept under control. Generation rejection at Jhakri hydroelectric power station subsequent to tripping of one or more evacuating feeders from. These are the type of scheme which are very typical to hydro station. Hydro station typically rely on, say, 2 lines evacuating full power or 4 lines evacuating full power, and tripping of one or more lines results into overloading of the balance lines. So special protection scheme at a hydropower stations is also one of the common feature. Load shedding in northern region or generation rejection in northern region as well as in eastern region subsequent to tripping of HVDC Balia Bhivanti Byport. This is a similar example where one power flow corridor, when it trips, you take action in different region also. Similarly, generation rejection in the hydropower station for Jhakri. So these are some of the examples, and there are a number of schemes now which are now commissioned subsequently to take care of various contingencies, and these are all custom built for each station and each area, and some of the schemes are wide area type of schemes, and in future these schemes can be even be based on the phasor measurement units which are taking measurement at one location and taking action on another location using the network of SCADA communication from the central load dispatch centers. These are some of the examples of which I have already described. These are the actually some experiences of backing down, etc. You can see when generation back down on Rian power station due to action of SPS during tripping of HVDC Rihan Dadri Bypole. One of the example which we have seen in earlier slide, and you can see how the generation was reduced to control the power flow. You can see Rihan Dadri on this corridor power flow from this level it has come down to 0 because of the tripping of this bipole, and again the generation was then reduced automatically to keep the line loadings under control. Yeah, so this is what on the special protection scheme. One of the special protection schemes is also islanding or isolation, controlled isolation scheme. So we'll see what islanding scheme basically constitutes. The islanding scheme consists of a set of under frequency relays and reverse power under frequency relays connected or tie points with the proposed island. So the first step of islanding scheme is basically to propose an island. So you say Delhi is an island to be created. Now first, once you decide the proposed island, then you identify how many points the proposed island is getting interconnected with the grid. And then depending on the generation which is dedicated to this island and the load, you then plan the balancing of the generation and load within the island. So this island can be then further split into separate islands of identified areas of generation and load. So if you are not able to manage host island, suppose Delhi as a whole, you island first by opening of the tie lines, and there are number of tie points with grid to which Delhi is connected. You have to keep certain generating units and its respective corridors connected to this island, isolated, and dedicate those generators, and the load will have to be balanced. So there will be under frequency and dF by dt load shedding schemes to keep the power balance between the available generation and the load which is connected. And if this balance results into further sinking of frequency, then you can split the island further. So maybe the North and South Delhi or West Delhi and some of the areas, depending on the configuration of the network, you can further split. One of the key features for deciding any sub area would again be availability of the generation in that area and the balancing of the load with that available generation. So again, there will be generation and load balancing to be done by load shedding and generation shedding, etc. So those schemes will have to be configured. In case of further frequency collapse, each generating station gets isolated with local loads, and further each unit go on house load if frequency further goes down. That means in spite of splitting of an island or creating sub-islands within the island, if the frequency continues to sink because load is higher than the generation, in that case, at least the generating stations should be then isolated from the load by bringing them to the house load. Idea here is you can, if you are operating on house load, the generation is available for reconnection very quickly. So the restoration of the island can be done faster. So that is the idea, and this is called then unit station islanding. So generating station itself can get islanded with whatever load. Again, this is many times very difficult for generating station to survive on house load because it is amounts to almost full load throw-off condition, and many generating stations, hydro especially, survival on full load throw-off becomes a challenge. So this load shedding by different means of under frequency as well as your dF by dt, the rate of change of frequency, becomes a crucial control measure to keep the balance between generation and load. Now, the success of survival depends on the quantum of load shedding in a pre-decided based on daily interchange which takes place with the from island to the grid. This interchange monitoring is one of the important success factor for the survival on land. This has to be done on daily basis, depending on the day's forecast of the load. You have to estimate how much power is being imported into the island from the grid, and then plan for quantum of load shedding so that post islanding, if islanding happens, the load and generation balance is achieved. Now, when islanding takes place, the rate of change of frequency can be very high. Frequency changes can be even 2 to 3 hertz per second. And it is necessary that such rate of change of frequency, the generating stations survive. So you should not have under frequency protection or other protection schemes acting instantaneously to trip the generator, because this fall in frequency and subsequently the rise due to the inertia as well as on the primary response of the generator should allow survival of the island. And that is basically the idea, so that appropriate time coordination should be done for survival of the island without tripping of the generator. One thing which we need to remember, the power number is very small during islanded condition. Yesterday I had mentioned that a power number for our complete interconnected Indian power system could be 14,000 or 15,000 megawatt for 1 hertz change in frequency. That means if you lose 14,000 megawatt, frequency may drop by 1 hertz. But when you get islanded, it may be just 100 megawatt or 50 megawatt may result into frequency varying by 1 hertz. So power number is very sensitive, and controlling the frequency in an islanded condition becomes a very big challenge, and the supplementary control in the governor then are needed so that frequency can be stabilized in an islanded condition. So very often you will have to change the governing mode from the load control or droop control to isochronous mode, where the speed controller will take care of the speed variation, which is a fast responding corrective action to keep the frequency in control. It is also important that before the actual island takes place, that means when you open the tie lines, before that adequate load shedding should happen. If load keeps hanging on, when you open the tie points, it's very likely that island will collapse because there will be very heavy load and the frequency will sink. Then you require supplementary control schemes like distress load shedding scheme. You require automatic load restoration schemes. That means after islanding, with the frequency starts rising, you should immediately put on certain load so that island frequency gets stabilized. The supplementary controls will have to be designed in the governor to recognize the isolated grid condition. Now, isolated grid condition by breaker input will not be possible perhaps locally because you are still interconnected with the grid, and as far as the powerhouse is concerned, it will governor will see as if it is connected to the interconnected grid, but actually you are operating in isolated mode. So there are again sort of islanding detection modules available based on the vector change or based on the frequency criteria, etc. And they need to then initiate the supplementary controls to keep the frequency under control. So this is the sort of overview of a islanding scheme, which has number of actions which are necessary for survival of the island. And that is one of the reasons why in our experience we see that though there are number of islanding schemes in service in India, the success rate of survival after islanding, there are very few cases, successful cases. One of the classic cases of good islanding scheme is of course Bombay, where number of times the islanding scheme has survived and kept the power supply for city of Bombay on even when the grid collapse had taken place. And of course there are other locations also, but it's a very complex phenomenon. These are some actual waveforms. You can see the frequency at a healthy level. Then there is some event because of the generation was lost, frequency collapse takes place, it comes down to very low value, it remains at this low value, and then there is a recovery. Islanding takes place. Once islanding takes place, there is enough load shedding, then the island will have surplus generation, so frequency will shoot up, and then the governing action will take place to stabilize at a new value. So this is a sort of a curve. You can see more in detail some of the events in here. This is a rate of change of frequency. You can see here it is 2.5 hertz per second. Frequency is collapsing. This graph remains below 47.5 level for almost 2.4 seconds. So it is necessary that no generating unit should trip, though the frequency is below 47.5. So 47.5 being the lower limit of turbine trip, there should be sufficient time delay so that this recovery is possible. Otherwise, your generating station will trip at this instant only, and island will collapse. So this is basically related to special protection schemes, and which include the island escape. Any question on this? We'll just can take one or two questions if that there. Okay, let us move to next. Now, we have seen grid collapse, contingencies, and the special control schemes, protection schemes. Now we come to restoration process. Essential feature of system restorations as per the SIGRE report, they are all applicable to Indian power conditions also. That network visibility, monitoring capability, and communication facility. So SCADA and communication becomes important. Proactive communication with all stakeholders, which includes government, customers, public, and neighboring system operators. So everybody should be aware of the grid collapse, and the restoration procedure should be known to all the constituents. Policies, codes, and defined organization structure, who will do what. Because again, multiple agencies are required during restoration process. Generating station, transmission station, and distribution companies all are involved, including major consumers, which might be in the restoration area. Multiple level and coordinated load shedding plans to mitigate the under frequency condition is a must. Restoration plans, periodically testing and training of the people. Recovery from total blackout, considering the black start facility, and also considering the distributed generating resources. Rules governing line energization and resynchronization. Post blackout, one of the important restoration process is how do you synchronize back with the rest of the grid. There are different approaches to restoration. There is a bottoms-up approach. Bottoms-up approach is basically where there is a number of dispersed generating units with black stars facility. So you start these small power stations, which includes hydro power stations, and then you build up power supply in a subsystem, and then interconnect different subsystems with each other synchronizing. So slowly go upwards to high voltage level. So this is a bottoms-up approach. That means you start from the small unit energizing local loads, and then subsystem, and then a number of subsystems which are in service. They take load in their own subsystem, and then they connect with each other, and then form a bigger system and slowly expand the system. The second, so this is the restoration which is the subsystem. And then synchronization of the subsystem, as I mentioned. Important aspect of this is in the given subsystem, which are the critical load which needs to be resumed, and whether we have capability to handle that sort of a load. For example, the main purpose of black start would be to provide startup power to the major power thermal power stations. One of the mandate for the hydropower station is to give startup power for a thermal power plant. And as part of the startup process, they have big motors like boiler feed pump, ID fans, FD fans, which needs to be started. So the generating unit which is used for black start and the controls which are necessary during this process to keep the frequency and voltage stable should have capability to take such a heavy startup of motors within the island. And the synchronization of various subsystems. That was the bottoms-up approach. Top-down approach is basically if there is a system available which is not collapsed, it could be a neighboring grid, the neighboring region where the startup power is available. So from the neighboring grid, it could you could get assistance, and that power then can be utilized to energize the lines and then start up the give startup power to the power station. This can also be sort of between not only within the region. That means if one northern region is say totally shut down, then eastern region or western region can provide startup power to the stations in northern region. So this is a sort of a top-down approach. That means you start with 400 kV and then go down to lower voltage at a distribution level. So that is top-down approach. Then next is the line charging guidelines during restoration. These are again some of the steps which are given in the NLDC Black Star procedure. Ensure that a line to be charged is free from fault before charging. Ensure that communication is available to both the ends. During restoration, lines of lower voltage level should be given first priority. That is the bottoms-up approach. The line should be charged from the end with higher fault level in order to limit the over voltage at the charging end. We had mentioned, especially if the line length is long. So when you charge the line for the first time, you may experience over voltage at the remote end. In case one bus is completely dead, charge the line from the other end, which is live, and close the breaker on dead bus. So you should have dead session. Otherwise, normally breaker will not be allowed to be closed without sync check. So the sync check scheme should have dead bus charging facility. Then the bus or line reactors may be kept in service as per the requirement with a breaker or isolated in closed position before charging the dead bus. If there are long line, then to control over voltages, we should have reactors all lined up so that over voltage can be controlled after charging. Likewise, there are procedures given. At the synchronizing end, control of standing phase angle to be less than equal to 20 degrees. That means to avoid jerk, heavy surge, power surge at the moment of synchronizing, to keep it to the minimum so the system do not, otherwise system may collapse again because you are already in the isolated grid mode and only a black start generator is feeding the area. So the angular difference should be kept under control, and the guideline is it should be within 20 degrees. Open end voltage should not exceed the voltage level for which the overvoltage protection operates. So it's necessary that overvoltage protections, which might be generally be kept at 110, should be properly time coordinated. If required during black start mode, maybe the time delays could be suitably increased to permit so the line should not trip on over voltage immediately after charging. So when you have the open end voltage too high, you charge the line at one end and the remote end voltage is too high, then charging of the wars, that means reactive power which is leading, it may be difficult for to survive with the over voltage. In that case, reactors and other control measures should be kept in service so that you don't face. So you line up the reactor and then charge the line with reactor already connected to the line. So dead line along with reactor you can charge. In some of the stations where the line lengths are large, it is a good practice to also line up the line on dead and then build up the voltage slowly by controlling the excitation on manual mode. So that is also being practiced. When one end you have a generating station and you have a line charging task. In AVR also there is a provision to have line charging capability where excitation can be built up slowly on manual mode to charge the line, so that you ensure that over voltages do not happen and the leading reactive can be absorbed by the generator as you build up the voltage slowly. So this is another way to control the voltages when you are doing the line charging. The thumb rule is synchronize or open from the end where line reactor is available. So wherever line reactor is available, use of line reactor is recommended. And then the black start operation. Those hydropower station where black start facility is available, they will be familiar with the black start operation. Typically, the key concerns is basically voltage and frequency control and controlling the line charging capability. As I mentioned that you will have different modes of starting. When you close the circuit breaker, you require permissive to close on dead line, and you will require permissive to close even for say not for governor to take a special supplementary control or to take on the frequency control mode, that is speed control mode. For example, if the most of the governor, they go under load control mode and pick up MW the moment circuit breaker is closed. Now you have to bypass that logic so that when the breaker is closed, line breaker is closed and excitation is being raised slowly, the governor will control the speed and will not go into load control mode. So these are some of the control changes in terms of operating philosophy will have to be done. This requires for each black start facility some study to be carried out in terms of voltage rise, etc. To take care of the Ferranti effect, as we mentioned, due to leading wars. Reactive power absorption capacity during line charging procedure. Step-by-step simulation of the black start plan can be done, and demonstration of the generation and load matching capability. And so the complete black start as a drill can be tried out periodically so that people get used to managing the black start and operating in a operating the sub area in an islanded mode with 1 or 2 generators in service. These are the various type of control functions which are necessary during the black start operation: load frequency control, voltage control, load rejection, large motor starting sequence in terms of their capacity, etc. Self-excitation assessment. Again, this is due to the leading reactive power being fed. The generator goes into self-excitation mode initially. Cold load pickup, system stability aspect, switching transient over voltages. Many times you face, especially if you have got a GIS, so GIS isolator operations along with the line capacitance, etc., can result into transient over voltages, which can be dangerous. And there are cases that failures have happened during the black start mode of operation. The control frequency, voltage control, load rejection during islanded operation, self-excitation, and black start drill, which is done periodically. These are some of the examples which are given on the paper which was published by the Eastern region. This is the black start facility trial at Tista power station. You can see how the voltage is built up in this case in step-by-step manner by manual excitation control. So you can see in steps voltage has been raised, and this gives that the blue line is actually the voltage at the generating station bus bar, and this purple color is actually remote end bus bar. So you can see the rise in voltages at the remote end compared to the sending end at this thing. So this is the rise in voltage, and step by step then it has been increased slowly to 400 kV level. You can see at the generating station end, the voltage is built up to the level of say 380, 395 kV or so. But at the remote end, voltage has risen to 410 level. Similarly, and when you suddenly change the frequency very wide, so here the frequency is 48.5 almost and up to 50.5. You can see the fluctuations. Whereas in the islanded mode of operation, the frequency is in the band of 49.5 to about 49. So these are the sort of fluctuations. So with a governor operating in isolated grid mode, it's possible to achieve this type of stable frequency. Similarly, this is the active and reactive power control. So you can see the active power. This is the reactive power at the bottom. So this type of changes will have to be handled during black start operation. This is again the frequency grid versus island frequency. You can see the grid. When you restored, you have to synchronize back with the grid. Now grid is quite stable in this blue color, but the islanded operation of the black start area, you can see the frequency fluctuation, and then you should bring in so that it can be synchronized at this point of time. So So this frequency was controlled, island frequency is controlled, and at this point then it is synchronized with the grid. So you can see various aspects of black start procedure. These are some of the lessons listed in the paper which was published by the Regional Power Committee. That free governing mode of operation is essential for stabilization of the island. The excitation control during initiation of the island has to be kept in manual control. Energization of the ICT has to be done at a reduced voltage rather than a rated voltage, so that the transient overvoltage during resonance could be contained at the lower value. The load type at each of the lower level feeders need to be known for stabilization. So when you resume the load step by step, you should be aware of their nature of the load. Synchronization should be done such that the smaller island frequency should be slightly higher compared to the larger island frequency. This is very important. The larger island will stabilize the incoming frequency from the small island. So in small island, which is driven by a black start unit, should have a slightly higher frequency when you are closing the breaker, so that the power flow can be accordingly. Otherwise, there will be surge of power from grid to the island, which island may not be able to sustain. Protection settings of all the elements of the station should be known to analyze any event properly. Communication is important. Reactive power plays a vital role. So this is basically summarizing the black start lessons. So this concludes our session. There are some of the papers of northern region as well as the southern region, eastern regions are there, which you can refer to, which summarizes the black start lessons. So we are also now on time for our first session in the morning. We can still have 5-10 minutes of questions if there are any. Yeah, so we conclude the morning session for today with this, and we are open for questions now. If there are no questions, you can discuss any experience and share for discussion purpose your experience on any of these topics.
पार्टिसिपेंट्स यदि कोई भी और क्वेश्चन नहीं है तो can you note down and ask question after completion of second session? Any response from participants?
Sir, power system stability. Hello.
Yes. Yes.
Sir, you have discussed the power system stability PSS.
Yes.
So what we have seen, sir, there is a steady state disturbance. Another one is transient disturbance, and third one is dynamic disturbance. So basically it is related with the voltage disturbance and frequency disturbance. And third one is, which I have seen, that is the angular, that is delta disturbance. So the voltage and frequency we can understand, but philosophically we cannot understand what is the angular displacement in the unstable operations of the alternator, sir.
Yeah. So yesterday when we talked about generator model, where we said depending on the load, there is a difference between EMF, which is open circuit voltage of the generator, and the terminal voltage when the load is taken. So the difference in magnitude and phase angle of the open circuit EMF and the terminal voltage of a loaded generator, the angular difference is called the load angle. Now, when there is a inter-area oscillation, basically what it sees is MW fluctuation as seen by the grid, but each generator is actually also accordingly expressing the delta, that is load angle oscillation. So your load angle will also oscillate in sympathetic to the generation MW oscillations, and this has to be damped out by the action of the power system stabilizer. Otherwise, it can lead to further instability if another some trigger happens, and that is the role played by the power system stabilizer. What it does is basically by changing the excitation in a given phase response, it damps out it acts as a damper to the oscillating frequency, and it will help in stabilizing of the entire power system. That is the role played by the, so MW oscillations of low frequency are not real. It is called a small signal instability. It's not transient, it's not dynamic. It comes into the third category of small signal instability, and it can be controlled by PSS. Yeah.
Sir, we are the electrical engineer, so it
Yes.
is very difficult to understand. Suppose the mechanical engineer can understand the inertia or something like that of the machines, but we know only the flux and that is the shaft torque and magnetic torque. So how we philosophically don't find out what exactly happening inside the rotor or electrical signal, how fluctuate when the disturbance is come as a steady state disturbance.
Yeah, basically, I think there is a analogy of electrical phenomena with mechanical phenomena for easy understanding of the electrical. If you rotor has two magnets, so there is a magnetic field created by the armature, which is stator, due to the current flowing in the stator winding, and there is a magnetic field produced by the field winding, and these two magnetic fields will be locked when you are having a steady state synchronized operation. That means the armature reaction magnetic field and the rotor excitation magnetic field. When the machine is synchronized, they are locked. When the disturbance happens, there is a slight slip between the, you can say, the magnetic lock which is there between the rotor and that is basically the phenomena of acceleration and deceleration for which is for mechanical understanding, and this oscillations in MW as a result of this angular instability also causes mechanical stress on the torsional space, specifically on the coupling of the shaft, and that's why it is sometimes dangerous for these oscillations if they are permitted to continue for a longer time. That's why there is a need to stabilize it and damp out as early as possible. This is a, you can say, the mechanical aspect of electromagnetic phenomena. The second aspect is, of course, from the grid stability perspective, because if this small MW oscillations as a result of load angle oscillations, again, load angle is the angular difference between the magnetic field of the stator and rotor. These oscillations, if they persist and any major system, another event taking place in the grid, the machines can lose stability and they can become out of step. In the afternoon, we'll also talk about out of step protection or pole slip protection for the generator, which causes actually more mechanical damage than the electrical damage. So, though we are electrical engineers, it is important to understand finally electrical current produces a magnetic field produces the mechanical force of attraction or deflection, and this mechanical force results into damage which is of the mechanical nature for say coupling or other thing, but at the same time it can damage the insulation also because of the mechanical. So all are correlated. So we as a power engineers or power station engineers should not isolate ourselves that this is mechanical, this is electrical. As long as there is a relationship of mechanical to electrical, electrical to mechanical, we should be aware of this phenomenon. Right? Am I able to clarify to some extent?
Yes, sir. Yes, sir. Sir, you have, yeah, sir, you have mentioned one things I have seen. Every 2 years the frequency range is reviewed from 49.7 to 50.2. Sir, what I have seen during commissioning of the TLDV4 project, there is a standard deviations. There's a standard fluctuations of the frequency 1%. So is it correct, or it is decided by the committee after 2 years? So what is the criteria to decide the grid frequency? This range should be maintained.
Deciding criteria is the actual experience of operating the power system. That is the job of POSOCO and NLDC and the regional load dispatch center. They, from monitoring this parameter continuously, they learn the lessons, how much control we have on various parameters, and they keep revising the guidelines so that this frequency band can be narrowed as much as possible. And what you are mentioning was a situation years back, but now the power system, especially with the situation that we have online reserve. Earlier, Indian power system never had a reserve. You know, whatever generation is online was fully utilized. There was no sort of a spinning reserve available in the grid. But now that spinning reserve is also available, it's possible to control the frequency in narrow band, and that's why they keep revising it. So all these operational parameters and their range of operation is again very dynamic, and it's not that every 2 years. It's as and when we feel the power system has changed, and now we can, there is a time to correct the situation, they amend it. So there is no fixed time. It all depends on your real-time experience and the availability of the resources at your disposal. Resources in terms of managing the MW and managing the reactive power. So whole game is basically of managing MW and MVR, which in turn affect the frequency and voltage. And then the commercial mechanisms and technical mechanisms are then some sort of tools in our hand to control the behavior of the power system. So both the tools are used, technical tools as well as the commercial tools. Both are used to control the parameter. So this all dynamic. So no fixed frequency of revision or something like that.
Yes, sir. Yes,
Sir.
sir.
Sir, I have a question.
Yeah.
Suppose a new power station is being commissioned, for example, 2000 megawatt Subansiri. What are the settings or some things need to be changed in other substation or power station so that the load flow and other characteristics can be set?
Yeah. So whenever there is a new power station getting commissioned, the system operator, which is our load dispatch center, and the regional power committees, they do carry out studies to see what will be its impact. Because the moment, say, 1000 megawatt power station is coming online, the line flows will change. The loading of the interconnection transformers will change. So the connection agreement which is made by the generation company with the transmission company basically spells out the conditions of that connection. So there is a regulatory mechanism by which a generating company has an agreement of connection with the transmission company. And it is onus is on the transmission company and generator company both to carry out necessary studies to see whether such a generation can be permitted to be connected. That's why this exercise is done well in advance, so that when the power station is commissioned, the line sometimes will have to be upgraded, or additional line will have to be built, maybe additional power transformers will have to be installed. So all that planning has to go hand in hand with the generating station planning. So evacuation of a power is a major component of planning along with the power station. So NHPC cannot plan power station in isolation without planning its evacuation. So the dialogue continues with the CTU and STU for evacuation when power station is required to be built, and studies are carried out for all type of power stations, whether it's a renewable energy power station, hydro power station, ultra mega power station for thermal unit. They all require the connection agreement with the transmission, and the transmission system will have to be augmented to ensure evacuation can be done in a safe manner. Right?
Yes, sir. Okay. But does this requires that some of the nearby stations or substations need to be updated also?
Yes.
Or some settings need to be changed?
Yes. And when the new power station gets connected to the grid, it also changes the fault level also. Not only it changes the load flows, it also changes the fault level. So all the especially the neighboring stations will have to review whether the fault levels are within control, within the rated capacity of the equipment. So this study includes all the connected stations.
Okay,
हेलो
sir, thanks.
Yeah.
सर एक क्वेश्चन है सर।
Yes.
मेरा नाम राजवीर सिंह, मैं रसूल से बोल रहा हूँ सर।
हाँ.
सर यहाँ प्रॉब्लम क्या है कि जैसे ही हमारी नवंबर से लेके मार्च तक जो हम बैरासुल पावर स्टेशन पे वोल्टेज बड़ी हाई हो जाती है सर। तो क्या हो रहा है कि जैसे हम मान लो अगर मशीन भी चलानी पड़ती है तो हमारी वोल्टेज तब भी बढ़ जाती है, क्योंकि हम एमवीआर को कंट्रोल करते हैं तो हमारी करंट बढ़ जाती है और करंट फिर हमें लोड भी कम करना पड़ता है अगर उसे और कंट्रोल करते हैं। कभी कभी तो सर हमारा 60 मेगावाट होने के बावजूद भी हमारी दोनों फीडर निकल जाते हैं, पोंग और जसूर। तो सर यहाँ अभी आरएमयू का वर्क हुआ है और ये प्रॉब्लम सर आज से नहीं है, जब से ये प्रोजेक्ट चालू हुआ तब से प्रॉब्लम है। तो सर
What is
यहाँ
the
ऐसा इसका
what is the voltage at which you are transmitting?
सर 220
220.
तो सर मैं चाहता हूँ कि सर इसका सॉल्यूशन क्या है और क्यों नहीं हुआ?
नहीं, again, the over voltage phenomena, which is mainly due to lightly loaded transmission network and reactive power, which is in excess, especially the leading reactive power. So it's a common problem of reactive power management during light load period and full load period. You will require some compensation. Now, whether it's a reactor compensation or any other method of compensation, again, this has to be mutually agreed. The lines are owned by the generating company or it is owned by the STU or CTU?
नहीं सर एनआरडीसी है।
नहीं, लाइन का ओनरशिप किसके पास है? सीटीयू के साथ है या मतलब पावर ग्रिड का है या स्टेट गवर्नमेंट का है?
पावर ग्रिड का है सर, पावर ग्रिड का है।
हाँ, तो ये पावर ग्रिड के साथ में डिस्कस करके what would be the best mitigation to control the over voltages will have to be studied, and after the study जो भी compensation लगाना है, static war compensation लगाना है या reactor लगाना है, that mutually you can decide, and regulated forum में capital expenditure accordingly will have to be approved by the regulator, either by the generating company or by the CTU, that is power grid, to put that investment so that voltage control can be done. So this is how the power system problems are to be resolved, and basically discussion forum is the regional power committee. In the regional power committee, you have to raise this issue, and then they will tell you how to approach and find the solution for this. Regional power committee also help you in carrying out the study also. If the over voltage study, depending on the light load condition and depending on the full load condition, that study also regional power committee will carry out for you. So you can take up this issue in the regional power committee forum.
Okay sir, thank you.
Okay, then now we can start the second session at 2:30, sir.
Yes.
And the rest of the question, if any, that can be asked in that session.